Hello and welcome to topic 8 in Introduction to AI, the series I've been working on. Making some progress, a lot to go, but we're up to making complex decisions. In our previous chat, we talked a little bit about making simple decisions. And the basic idea there was to establish some ground rules on how we decide to make decisions in an intelligent way and potentially have intelligent agents making decisions intelligently. As always, a good resource here on the screen, the inside of Berkeley, their AI ML group is really solid. So when we think about making decisions, there's various types of them. One of them is a sequential decision problem. Um, and when we talk about this, we talk about potentially things like a Markov decision process. And it's defined by a set of states as that belong to all possible states, and a set of actions that are also of all the actions that are available, and transition functions that take in a state and an action and return back a state prime, or a state that has been modified, so it leads to that state. Um, and these are also called model or dynamics. So when we talk about how do you move from one state to another, that's being done here through action. So essentially, you're taking a state, you're applying an action to it, and resulting in an output. Um, and there's a reward function, which is takes in a state, an action, and a state prime, or sometimes it just takes in states, such as the state or state prime. And then, as with most state transitions, there's a starting state and possibly a terminal state. So there may be lots of different ways you can look at this. So moving on to how we get into it into more. So what's this whole Markov bit about, right? And when we talk about these Markov decision processes, or MDPs, what's a Markov? And it generally means that given the present state, the future and past states are independent, meaning that each of the actions are essentially independent. Or more precisely, the state that has resulted because of an action is independent. So that means that no outcomes depend only on the current state. Sorry to restate that. Given your current state, the next state depends only upon that state and the action, right? So there's no additional things like what was the previous state that occurred. It's just like search. Where there's a successor function that could only depend upon the current state, not the history. So at the end of it all, if you look at this, it doesn't matter how the little robot got into this cell. It's in the cell. The states that it can go to don't depend upon how it got there, only on where it is. So, and in this case, it clearly, if it isn't the initial state, came from some other state. So when we talk about policies, so when you deal about deterministic state, single agent search problems, a lot of quantifiers going on there, right? Deterministic means that you can figure it out. There's only a single agent and it's a search problem. We want an optimal plan or a sequence of actions from start to goal. So, and more precisely, you're walking your way from some initial state, which is of the overall state, to some goal in the best way. So the policy pie gives you an action for each state. An optimal policy is one that maximizes the expected utility it followed, right? And explicit policy defines a reflex agent. And so there's going to be likely one or more optimal paths, and it essentially comes up with how you're going to get there. And you can see kind of here what those are. And this is, anyway, so we talk about utilities of sequences. what is the preference an agent should have over a reward sequence? Is it more or less, and so on? So you may also want to think about when you're determining which one of those to go on, um, which is the better to try to get the higher reward sooner or later in the process. Concept of discounting is basically the idea that it's reasonable to maximize the sum of rewards. It's also reasonable to prefer a reward now to rewards later. So one solution is to value of rewards decay exponentially. So you start off trying to encourage action, if you will, versus inaction. Part of this also comes down to the concept that information potentially has value, and that value may also degrade quickly because it also it comes down to it's the older something is, the less important it likely is. So when we talk about how do you discount it, each time we descend a level, we multiply in the discount once. Why are we doing it? To some extent, you're trying to encourage behavior, right, is what it comes down to. But you can think of it as a gamma chance of ending the process at every step. Helps our algorithms converge. And so you may start off with a discount of 0.5. And what do you do if it lasts forever? It's possible that you may not have something that essentially leads to termination, or you may not get a convergence so that you come to a single solution. So instead, we want to somehow have something built in to help with that. And it comes down to you may come up with a fixed number of intervals of t, essentially a life expectancy, and a non-stationary policy. So pi depends upon the time that is left, right? So your basic idea is to almost put a countdown timer, if you will, onto the overall searching algorithm. So when we talk about Markov or algorithms for MDP, an example is racing. So let's assume we've got a robot car wants to travel quickly, fast, right? So you've got three states: cool, warm, or overheated. You got two actions: slow or fast. Going faster gets double the reward. So you end up with a race, essentially a search tree for your race, with the various cases that you could end up with of going fast or what's the other, slow. And so obviously when you go fast, you're going to overheat your car eventually, is the basic idea. So whenever you come up with these various state projects, you end up with a expecting max like search tree, where you're going through and looking for various states, and you're essentially kind of defining the MDP as a Markov decision process with a set of S states that has an initial state S0, a set of actions, some transitions, and a reward associated with the various states, as well as potentially an action discount. And so you basically have policies as well, your choice of action for each state, and the utility, the sum of discounted rewards. When we go to solve these things, it's essentially going to be drilling through until you you're going to try to eliminate stuff as quickly as we can, is what we're getting at here. You're doing way too much work. So we need to come up with a better way of doing this. And also states will repeat and the tree goes on forever, right? So lots of challenges with that approach. And so we then may be better off doing a recursive definition of our value, so that we're basically able to recursively define and then limit these approaches, these algorithms with time, so that they have a certain amount of time to run based upon the way that the value is going to decrease, simplify each one of the layers to the various states, and then moving on to value iteration. We start off with the number of steps, and you try to repeat until there's convergence. I'm going to go through this quickly because I want to get back to other topics. There's other classes of problems. Some of these we could call bandit problems, in part of the one-armed bandit being a slot machine. There's typically some sort of way of defining their states with probabilities. There's not going to be a discount for this particular class of problems. And both states have the same value. So when you start playing, you can see that, and also you may want to potentially start changing some rules and you may also figure out if something is an unfair machine, which is something that can happen. And we're dealing here with partially observable Markov decision processes. And the idea is that you can see some of what's going on inside of it, but there's that unobservable portion as well. Anyway, with that, we'll wrap this up. A bit of an interesting decision, relevant if you're drilling into solving problems, especially complex ones, understanding that there are oftentimes various types of heuristics that we want to utilize to come to closure and to reach a solution. As always, thanks for watching. Let me know what you think, and I look forward to talking with you soon.